And we're on, all right. So back in weeks 6 and 7, after we did the probability, we played with the idea of confidence intervals using sampling distributions with a simulator called StatKey, and then we proceeded to do simulations for hypothesis tests. So that's like rolling the dice over and over again to try and figure out what the probabilities are, which is fine and appropriate, and sometimes that's the only choice when it comes to exploring reality by doing experiments. But there's this theory behind it. Like with a dice, we have the theory that 1/6 the time we should see the number 4. Now that's a theory. If we had all dice rolls ever rolled and ever to be rolled, then we would see exactly 1/6 of them, but that's not possible. So the reality and the theory are related, obviously. The theory is ideal. It's like finding a perfect circle in nature. One does not exist. It's just this idealized form our minds have kind of developed from what we experience. And so now we're going to take the theory of normal distributions, excuse me, and the central limit theorem, which give us some formulas and equations, and we're going to apply those to the confidence intervals and hypothesis tests. So now basically we have 2 ways to come up with hypothesis tests results and 2 ways to come up with confidence intervals. So I'm just going to kind of draw a flow chart of what we have for inferential statistics so far and a few of the formulas, and then we'll apply them to a few problems. And let's see, we have a new visitor. Cool. All right, so whiteboard. And good morning, Jennifer. So here's kind of the overview of inferential statistics. So there's essentially 2 parts to statistics. Descriptive statistics, where you get data and you make calculations like mean, median, mode, standard deviation, and you make pretty charts and graphs. That part of statistics is important, and we covered most of it in 3 weeks. Inferential statistics is the idea of using data, using samples to make predictions about populations, and inferential statistics is a vast, vast subject. That's the majority of what statistics is really about. And people spend, like they get PhDs in just inferential statistics. But descriptive statistics, that's like 3 or 4 weeks of stuff to learn. So we're scratching the surface of the real big part of statistics. So for us, we have 2 main parts of inferential statistics. Either we're trying to find some value about a population, and that's when we make a confidence interval. And so again, here we're trying to identify a population parameter. Okay, so that's one part, and that's done all the time, especially for public opinion surveys. We want to know, well, what do people feel about things, or what do people believe about things right now? The other part of inferential statistics we've explored is the idea of testing something we thought we knew about a population parameter, and that's the idea of a hypothesis test. And in this case, we're trying to test a value of a population parameter. Whoa, what happened to my pen? Stop it. Interesting. Let's try that again. So for example, there's a lot of unrest right now related to some recent deaths in society in the US, and there's all these marches going on. And how do people feel about the National Guard being called in to help maintain order? So we don't know. We're going to have to ask a lot of people and figure that out. We might have some biased belief based on our preconceived ideas that, yeah, we should throw in the National Guard, and everybody else agrees with me, and somebody else might say, oh, no, we shouldn't do that. And everybody else agrees with me because I hang around with people that believe the same things as me, right? We're all biased. So we have to find ways to measure these things. So again, identify some unknown information. And then otherwise, somebody might say, hey, it's 50% of people think we shouldn't use the National Guard. Okay, well, let's take a sample and double check to see if that's really true. So a hypothesis test tries to take some given information and say, is it really true or not? Does the data support it? Does the data not support it? Do we reject the null? Do we fail to reject? So testing existing information. Okay. So once we decide which branch we're on, what kind of problem we're trying to solve, then we have to decide in each of these, are we playing with a mean or a proportion? Now there's tons of other parameters to measure, like standard deviation, the median, percentiles, and things like that, the range of values that you could get for a certain measurement. So there's tons of parameters one could measure. We're only focusing on means and proportions. And again, if you were in some subject where you needed to explore more than that, then you would get more statistics in your background. So once we decide, hey, yeah, I'm doing a confidence interval, then we want to know, are we working with a mean or are we working with a proportion? Okay, so like the percentage of people who think it's okay to use the National Guard to deal with these marches, this public unrest over what's going on right now. Now, as far as a mean, there's a couple of things to consider about the mean. So that breaks, let's see, now I guess I want to stick with, no, I'm going to use two different colors. There's two different parts we might explore as far as the mean goes. And for the mean, remember the symbol sigma stands for the population standard deviation. And so the question is, do we know the population standard deviation, right? And I shouldn't put a question mark there. Let's say we do know it. The other scenario is where we do not know. So don't know sigma, which again is the population standard deviation. Now think about this for a second. We're trying to measure a population mean. If we don't know the mean, how would we know the standard deviation? So although in statistics class like this, it's usually taught this way first, kind of because it's easier, in reality, it turns out this branch doesn't hardly exist. So we're not going to, we've gone down this branch a little bit. We will this week, but it's not going to be very much used. Otherwise, we don't know it. If we think we do know it, then we're going to use a normal distribution. And if we don't know the population standard deviation, we're going to use what's called a t distribution. That's a funky T. Let's try that again. T distribution. And so more often we're going to use the t distribution. And the t distribution is kind of cool. It was developed a little over 100 years ago by a guy that was working for the Guinness Brewery, trying to maintain quality with a small number of samples to try and figure out if they were doing a good job making the beer, what conditions were right for the yeast, how they reproduced the yeast, all these different things that go into making a beer consistent. It's very hard. And so 120 years ago, people were working seriously on this kind of problem, and mathematicians or people that knew a lot of math worked for these companies, way back then, trying to make sure they had something good people wanted. And the t-distribution came from that, which is kind of neat. So formulas, if we end up down these paths, are for a, let's see, we're under confidence interval. We have a margin of error. So the error bound on the mean is what we care about most here. That would be a particular z-score that we have to calculate times the population standard deviation divided by the square root of n, according to the central limit theorem we learned last week. The t is pretty similar. If we happen to not know the population standard deviation, then we have to calculate a t-score, and we'll look at how to do that in a moment. And since we don't know sigma, we have to use s, which is the sample standard deviation, and then divide by the square root of n. So notice these formulas are pretty similar. A z-score counts standard deviations. A t-score does it in a slightly different way, but similar. Then we have a standard deviation, and then we have square root of n, okay? and mostly we'll end up down this path here. So if we don't know the standard deviation of the population, and another case we'll use this is for small sample sizes. So the central limit theorem says even if you know the standard deviation of the population, you still want to have a sample size n that's greater than or equal to 30. It turns out that even if you know the sample standard deviation, if you have a small sample size, you're not allowed to use a normal distribution, so you use a t-distribution instead. So over here, another case will come down this branch is if n happens to be less than 30. Oops, that didn't come out right over there. So this is kind of a flow chart about how to proceed. And the flow chart still kind of applies to the way we did things in StatKey. It's just in StatKey, we don't need these formulas here. StatKey does the computations for us accidentally on purpose, which is kind of neat. All right, so again, this is, oh, this blue thing right here, by the way, I didn't label it, is the error bound on the mean when we don't know the standard deviation of the population or the sample size is small. As far as proportions go, we had a rule about the proportion that the successes, which is the probability of a success times the number of total outcomes, the book called this X also, that number has to be greater than 5. And the number of failures also has to be greater than 5. And that would be Q times N. So if these two conditions are true, then we can proceed. If those aren't true, then we're stuck. We can't do it without some other kind of statistics that we haven't explored. It's in a whole nother course. And Q, remember, is always 1 minus P. And then to calculate the error bound on the proportion, then we're going to take the appropriate z-score, which is kind of the same thing as the z-score in red over here, and multiply by the square root of P times P prime, because it's a sample, Q prime over N. And all of that is inside the root. Redraw that better. Start it like that and put parentheses, P prime, Q prime over N, close the square root. And yeah, so then we got to learn how to find the z-score, how to find that t-score. And I don't think I'm going to fit it in this screen right here, but we'll find that next. All right, so otherwise, if it's not a confidence interval that we're doing, I'm just going to kind of draw a little line down here, separating these two. In a hypothesis test, it's either a hypothesis test for a mean or a hypothesis test for a proportion. And then kind of like the confidence interval, either we know sigma or we don't know sigma. Oops, I didn't want that to be in red. So I'm putting that in red just to indicate that often, come on eraser, often if we're questioning the mean or we don't know it, how the hell would we know the standard deviation, right? It just doesn't make sense. But it's taught that way because it more easily relates to the central limit theorem, which is a little bit complicated. So let's see, this is again, don't. No, sigma. And remember, sigma is the population standard deviation, not the sample standard deviation, not the sampling distribution standard deviation. Those are 3 different things that are related. Okay, so let's see, what else do we need to know here? If it's a hypothesis test, then we need to know the standard error, which is standard deviation of the sampling distribution. And let's see, what else do we need? I guess that's the main thing we need to know there. Standard error, SE, and that would just be sigma over the square root of n. And we're using a normal distribution. If we don't know sigma, then the standard error is the sample standard deviation over the square root of n, right? Notice same thing that's going on over here. This is my standard error right there, s over the square root of n. So if I don't know, I need that right there, and this is from a t distribution instead. And we can either use a stat key or a spreadsheet to do normals and t distribution calculations, which we started working on last week. Anything else I need to mention there? I think that's good. And again, with the hypothesis test, the main thing we're trying to figure out is what's the p-value. And I'll review what a p-value is in a moment. Proportions, same rule over here, successes and failures have to be greater than 5. So as long as NP is greater than 5 and NQ is greater than 5, and again, these are successes and failures that are counted. Oops, missing the letter there. So if that's true, if I can check off those boxes, then I can proceed. And then here, I need to know the standard error. And in this case, the standard error is going to be P times Q divided by N. And all of that is in the square root. And notice that almost the same thing as over here. Notice in the confidence interval, it's a P prime Q prime. And the importance of that right there, those are sample values. If we're talking about a confidence interval, and if we're talking about a hypothesis test, then it's important that we switch these to the population values, the population parameters. And hey, Dawson, I didn't get to welcome you. How you doing? Welcome to class. So this is a flow chart of the major things that we've covered in the last 4 weeks, including this week. No, 4 weeks. 4 weeks, including this week, yeah. And we were doing this already in week 6 and 7. We just weren't using these formulas down here. And I don't know if you can see what I'm pointing at here. So we were doing all of this in week 6 and 7. So this is week 6 stuff. This is week 7 stuff. In week 8, we just added these formulas in addition to using stat key. So before we were bound to stat key, we didn't have any other way to proceed to do a confidence interval or a hypothesis test. Now we don't need stat key anymore, but we can still use it if we wanted to. So we have 2 ways to make this stuff happen. And now that computers are so powerful and everybody has a computer in their pocket, simulations are gaining ground in the way to do statistics. Because it's easy to generate millions and billions of simulated samples with a computer to kind of test out what we think is going on in reality. All right, so we're going to put this information to use with a couple of examples. So I'm going to go grab some things from the homework. And I saw a bunch of you dove into the homework. I'm sorry it took me so long to get that going. Again, this new environment requires me to redo some stuff for us all. All right, week 9, yes, week 9. And then this week is a little bit different. This is, there's not gonna be an application like before. So what I did is I picked some of the more basic problems for the practice and then some of the tougher problems I'm calling the application, but they're really both just practice stuff that you can redo over and over again. So there's no assignment this week where you just get one shot at it. It's just all practice stuff. So that's these 2 assignments here. And then the critical thinking this week is a bit different. In my experience being a college student and a college teacher, I've learned that preparation is the most important thing. And so what I'd like you to do is go through your notes, go through the book, and make a summary page or two of all the important things you need. Like this thing I just drew here. This covers the last 4 weeks in one drawing. Now it's missing a few things, like I haven't, in this case, I lost my mouse, there we go. We need to figure out how we calculate the z-score, how we calculate that t-score. And so I'm gonna go over that next. But this has all, like, this is huge. You want this in your notes, for sure. Because it's a flow chart to help you figure out what formula do I use this time, shit. And so you just say, oh, I got to figure out a parameter. That means I want a confidence interval, and it's a proportion, so I should use this formula. Okay, so it kind of leads you on the path that gets you the right place. I think I want to start with the applications. And continue. Okay, so let me see. So we have some formulas. Yeah, so I tried to break it down into, let's see, is this the one I set pages on? Does I have a next page at the bottom, or is it all one page? Looks like it might, oops, what are you doing there? Go away. Looks like it's all on one page, 12 problems. 12 problems, okay. So there should be headings in different parts to say, okay, switch to these formulas now. Did I get that in here right? Oh yeah, there's another heading. And is that the last one? Yeah, okay. Again, notice here I don't even show that red branch. Over here I just show, is that true? Let me see, am I lying? Yeah, mean and a proportion. I just go straight to the, either we're gonna use a t-dist or we're gonna use the proportion stuff. So yeah, this looks like a good one right here. So we'll do this in a couple of different ways. We'll do it the stat key way, and then we'll do it the, so my question number one is gonna be similar to yours, except you're gonna get a different set of temperatures here. And then we'll do it the flowchart way in just a second. So first thing I'm gonna do is I'm gonna highlight these, and I'm told down here, I wanna find a 98% confidence interval. Up here it says you must estimate the mean temperature in degrees Fahrenheit from the following samples. Okay, so we have the temperatures of something, and we want to say, okay, well, what's going to be the average temperature for this, whatever we're measuring. Stat key. Oh, I had a link to it right there. And confidence interval for a mean, right? We're definitely doing a mean here. Make sure we're on the right page. And edit data, and hopefully I copied that correctly, and it will just paste in there. Didn't copy it correctly. Try that again. And you want to be careful not to copy too much on the web page, otherwise it'll paste in funky. That looks okay. Notice I do not have a header, so you got to pay attention to these, otherwise you get the wrong values. It miscalculates. And it says I have 12, double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep. And so then the member confidence intervals, we did this 3 weeks ago. We get the data in there, and then we just hit generate, generate, generate. And we want at least 6,000 samples. So again, what StatKey is doing here is creating what's called a sampling distribution. And a sampling distribution means take this sample here, make a deck of cards, and then give me 7,000 more samples of size 12 based on that deck of cards. And everyone's going to be a little bit different. Like these cards over here got drawn more often than these cards down here. So I have a mean that's in the higher end. But it could be the lower cards got drawn more, so I get a mean in the lower end. But notice that this does have that bell shape, which is kind of remarkable that we always get this bell shape. We're doing a confidence interval, which is always two-tailed, and then we have to get the right confidence level in the middle. 98% for mine. Double check what yours is. So 0.98 as a decimal. And then it gives me this down here. So let's put this in my spreadsheet. New page, please. And screenshot it. And all I really care about is the graph and the numbers at the bottom. And then I'm going to redraw this, add to current page. All right. Let's put you up higher and just a tiny bit smaller so I can fit my drawing in. So what am I measuring here? Temperatures. And they look like degrees Fahrenheit to me. Oops. Did it say in the problem? Yep, Fahrenheit. In degrees Fahrenheit, and we are trying to estimate the mean. So here's our point estimate. So we think that based on this X bar, we think that's approximately the population mean. According to the central limit theorem, they should be about the same. And we believe that's 49.511 degrees Fahrenheit. Now, the other thing is we can never be sure that's the population mean. It could be any number in here, and actually it could be outside. I'm never 100% sure. So we have an so this again is a point estimate right here. Some review of terminology. We also can make an interval estimate. So our interval estimate is going to be a low of 43.429 and a high of 55.600. So we're 98% confident that the average temperature of this scenario is somewhere between 43 degrees and 56-ish degrees. And then we can also find the margin of error. So let's do that. And the recommended way to find the margin of error from stat key, so let's put that over here, I guess. So the error bound on the mean is to subtract these numbers, or sorry, yeah, subtract them, right? Find the distance and then divide by 2. So what is 55.6 minus 43.429, and then cut it in half, right? So we take the whole width and we find half of it, which is similar to taking the upper number minus the middle or the middle number minus the lower, but because of this is a simulation, it's not perfectly symmetric. So this is the safer way to do it. So 43.429 calculator time. So parentheses 55.6 minus 43.429. Double check I typed those right. Yep. And then divide by 2. So close parentheses, divide by 2, and blow that up. So there's my calculation, 55.6 minus 43.429, cut it in half. So I have a margin of error of 6.0855. So I could also say we believe that the average temperature is 49.511 plus or minus the 6 degrees. So we're within 6 degrees of 49. Okay, so a couple of ways I could state that. But first I want to draw my version of this just for practice. And you should always draw one of these on your paper when you're doing these problems. So in the middle goes the point estimate, the 49.511. And then we mark off our edges, 43.429. That's my lower estimate, and my upper 55.6. And then I'm going to make a note of the margin of error here. So that's X bar. And the error bound on the mean, which I could have drawn on this side too, it should be the same, is that 6.0855. And I should also write in here that this was a 98% confidence interval, and I could throw the tail probabilities in here too. And again, this would be my estimate, oops. Of the average temperature. Just to be clear on a couple of things, I think the average value of any possible temperature for this situation is somewhere between 43.4 and 55.6 is what we've calculated here. An individual temperature, like maybe these are daily temperatures in a particular month in some area, individual daily temperatures could be vastly outside of this interval. I'm looking at averages, and the range of an average is always going to be much smaller than the range of any individual number in the data set. So those are two different things, and they're easy to confuse. And when I've been grading the confidence intervals and hypothesis test, there's been lots of confusion on that, and I try to make a note to you when I think you might have confused those two ideas. But my point here is, again, look at these numbers right here. They're from the middle, they're 6 apart. But if we look at the original data sets, we can see there's a much wider range. Whoa, I didn't mean to hit that. Back here. So let's see. They don't give me a lot of summary statistics here. I can kind of look at it and guess. Oh, yeah, the picture kind of shows me. Yeah, so here I have a low of 35.9 and a high of 62, okay? And again, compare those to my confidence interval, which is 43 to 55. So the range of individual numbers is always going to be vastly greater than the range for an average. Because remember, the average, what does it do? It sucks in the min and the max, and we forget about them, okay? So it really compresses data when you do averages. So confidence interval is going to always be a tiny range compared to the range of all possible data values from individuals. All right, let's do this spreadsheet style. So let's go to my drive. And we're going to redo these problems with the formulas from that flow chart. I think I need a new sheet for this. Same stuff I'm going to do here works in Excel. So if you're whipping out Excel now, I highly recommend you play along. Okay, so inferential stats, overview, review. And this is problem number 1 from the applications. So I need this data. And notice this is a small data set. I'm doing a mean, so I can't use a normal distribution. I have to use a t-distribution according to my flow chart here. And I will post this flow chart. Where'd it go? Back a couple pages. Yeah, that flow chart right there. So if you didn't get that in your notes, then I will post this so everyone can get it. And I highly recommend you redraw it instead of printing mine. So we have temperatures in Fahrenheit. Get those, and you should label everything, very important. This is app 1 down there. All right, so a couple of notes here. I have a small sample, and I was given no information about the population standard deviation. So that is sigma, not known. And those pieces of information imply use t-dist, not the normal dist. And let me blow that up a little more. Hopefully that's readable. And let's see, I don't think I need that up there. Okay, so this is just some notes to me to figure out where I am in my flow of what I know about information in the inferential statistics. So I'm estimating a parameter, right? So they asked me to identify a parameter, and I'm doing a mean, and I don't know sigma, and the sample size is small. Okay, so I'm in this branch right here. So I'm going to have to apply this formula here, where I take a t-score times the sample standard deviation divided by the square root of sample size to get the margin of error. So let's build that. So known information. So we have the sample data next to us. I need to know the confidence level. So confidence level, and that was given to me as 98%, I believe was mine. Right away, you should draw your picture. So can I get a screenshot of my picture in here? Because that's going to help me figure this out. I guess not easily. Get back here, where'd you go? I'm going to start a new picture. So on a piece of paper, you should be sketching this out. And I'm taking not the stat key approach, but the spreadsheet approach. So I'm just going to start over with my picture. So again, what am I trying to do? Estimate average temp mu. And drawing a rough normal. I need to figure out what is X bar, because that's going to be the center of my confidence interval. I am doing a confidence interval for this estimate. And I want to figure out what is the error bound on the proportion so I can get this upper number and this lower number over here, such that 98% of other samples like this one would be in the middle. What's the lower end of averages? What's the upper end? And this says, my formula from the flowchart says find the right t-score and then take the sample standard deviation, divide by the square root of n for that calculation. To find the t-score, I need to do a t-dist. So I need to get a t-value that goes with this lower number here. And to find a t-value based on a percentage, this 1% up here, I'm going to use what's called an inverse t. And I think, let's see, the Excel formula I think is just inverse.t. Let's go double check, or the Google Sheets. So let's see, I need to know my tail probability, which we call alpha over 2. And so that would be equal to, I need to know what is the tail. So the tail would be 1 minus this percent up there. And then I want half of that. And I want that as a percentage. And I don't need any decimals. So back in my notebook, I know that the confidence level is 98%. Alpha is always 1 minus the confidence level. So that would be 1 minus 0.98, which is 0.02. And the tail probability here is always alpha over 2. So next I need to calculate alpha over 2. And I just did that in one shot in the spreadsheet. So what is this? 0.02 over 2. So altogether, we could say the formula for alpha over 2 is to take 1 minus the confidence level and then divide by 2. And on a calculator, that numerator is going to be in parentheses. And sometimes on my spreadsheet, I'll have both alpha calculated and alpha over 2, so I don't have to worry about parentheses. So just to do it that way for fun, we'll just call this alpha. Alpha is always 1 minus the confidence level. And whether you want to leave it as a percent or a decimal, that's up to you. And then I need the left or the right tail. They're both the same, so that's what we call alpha over 2. And you may remember seeing this in the book way back 3 weeks ago, equals this number over 2. Once I have that information, I also need information from the sample. And from the sample, I need to know what's the sample size, n, what's the mean of the sample, and what's the standard deviation of the sample. So let's get those numbers here. Let's highlight those. There's my highlighter right there. So just to double check, it's always a good idea to have the computer count, because I'm always miscounting things when I point to stuff and try to do it. Confirms there were 12, average of the data, and standard deviation. And I recommend the .s version. Okay. All right, so then for the sampling distribution, I need to calculate what we call the standard error, which is a standard deviation. And back to my flow chart. The flow chart says, that's this value right here. Let's highlight that. And then we have to calculate the t-score. All right, so the standard error here is going to be the sample standard deviation divided by the SQRT of the sample size there. And then I need to know the appropriate t-score. And I believe that's, let's see, t dot inverse. Okay, that's the one I want right there, I think. It's not giving me the description of it. There we go. Calculates the negative inverse one-tailed t-dist. Yes, that is what I want, one-tailed. So then it says, okay, what's your one-tail probability? So that was that alpha over 2 up here. And then it says, hey, what are your degrees of freedom? Degrees of freedom is always 1 less than the sample size. It's always n minus 1. I'll put this in the notes. So I want to go get that sample size and take away 1 from it. And that gives me my t-score, and it always gives me the -1. And the t-score is like a z-score, so let's put that in the notes. Next. Okay, so to calculate the t here, red, I'm going to use the t.inv formula. And the TINV wants to know what's that tail probability. So that's my alpha over 2 value. And then it wants to know what's the sample size minus 1. Okay. So in this case, I entered the calculation from, that was that 0.02 here. Oh no, oops, I didn't write it down. That one, alpha over 2, and then an 11. So all it needs to know is what's the sample size minus 1 and what's the tail probability here. And a t-score is like a z-score. The middle z-score is always 0. You haven't gone anywhere from the mean. And then it counts how many standard deviations are you down the line. So on this side, your t-score is always going to be a negative number. And on this side, the t-score with the upper is always going to be a positive number. Okay, and all I want is the positive version, even though it gives me the -1. So we'll have to tweak that. So back here, so I'm just going to sneak into this formula right here, and I'm in between, or I guess out to the edge here, I could just multiply this by -1. No, I'm going to go in front of the equals and sneak it in. I'm going to say, give me the opposite of that. Okay, so I got that number here. That these are both about 2.7 is a coincidence. So then the error bound on the mean, in this case, is equal to the t-score times the standard error. And so altogether, that number right there is, let's see, the t-score times the sample standard deviation divided by the SQRT of the sample size. Let me separate that out a little bit to make it readable. So that's the calculation I just made right there. And to do that, I needed to know the sample data and the confidence level to figure that out. So notice this one is a little wider, 7.4 instead of the 6.1-ish that I got earlier. And the t distribution kind of does that on purpose. Since we don't know the population spread, the t distribution says, let's just make it a tiny bit wider, because we don't know so much. Not only do we not know the mean, but we don't know the standard deviation of the population. So let's make our net a bit bigger. And that's the safer thing to do here. But you don't want to make it too big, so the t distribution kind of splits the difference. It says, okay, let's look a little bit farther out for the population mean, but let's not go too far, otherwise we have a useless estimate. Once I have that, then I can get my interval, because notice I have some important things here. Let's use bold. We have the mean here, the center value, bold, and we have the margin of error here. And that gives me my interval. So I'm just going to round these numbers. Let's see, did the problem say where to round? Accurate to 1 decimal place. Now, normally I would say 2 decimal places because the data has 1, and usually with statistics we go 1 more. Let me read the fine print. Find a 98% confidence interval, accurate to 2 decimal places. I'm stating the reason there, sorry. Helps if I read the whole sentence. Yeah, 2 decimal places. Usually with statistics, we go 1 more than the data. Data had 1, we state 2. All right, so back here, so I'm gonna report my mean as 49.56. So let's get that in the notes. There we go. So I'm just gonna redraw that picture there. .56 is my center, and I now have a margin of error, which is what, 7.45. So this is my X bar and my error bound on the mean, 7.45. So then I can add the 7.5 to this side to get the upper, and I can subtract the 7.45 to get the lower over there. That's the last thing we do on the spreadsheet. So lower and upper equals the mean minus the margin of error, and then equals the mean plus the margin of error. And so what do I get? 42.11, 57.01. I get that right in my head again. 42.57, okay. .11, 57.01. So that's my confidence interval. So then I'd write my sentence. I'm 98% confident that the average temperature is somewhere between 42.11 degrees Fahrenheit and 57.01. And this problem should take either, now notice that's a slightly different answer than I had from StatKey, but they're in the ballpark of each other. 43 to 56-ish. And 42 to 57-ish. So the t distribution always goes just a little bit wider to accommodate the fact that we do not know the standard deviation of the population. Okay. Sorry, homeschool interruption. Yes, dear. Okay, sounds good. And this is the last week of public school, so I don't know about any of your households, but we are frantically trying to get our kids to get the last of their work done this week so they can survive school. Very exciting. I had a ton of teenagers here last night asking lots of math questions and grammar. I'm not very good at English grammar. All right, so let's enter my number. I'm going to go with the central limit theorem version of this right here, which was the 40. Oh, yours was last week, Brenda-Lee. Okay, thanks. That's very exciting here. It's going to be a wild week. 42, I think it was 42.11 central limit theorem version and 57.01 if I remember right. Wish me luck. Yay, I got it right. Woohoo. So if you just did this problem with me, I'd recommend doing it again. As far as the spreadsheet I set up here, I have a similar one set up for you to just kind of plug stuff into if you want to try it. So I probably should show that quick here. There's a lot of resources this week and we'll go through them all. So this is a week where you might want to try and attend every day if you can, these sessions, because we're getting ready for the final here, putting everything together. So there were a couple of things, yeah. So model confidence interval with spreadsheets, and then I have hypothesis tests with spreadsheets. And so I have pre-built spreadsheets you can just kind of plug your own stuff into. And then as far as you using those, if you're a Google user, you'll have to go to the file menu and choose make a copy. So actually, let me go take this into an incognito screen. Open an incognito. So it'll look more like this for you when you open it. If you're signed into Google, then it will say down here, make a copy, and you should be able to click that. If you're an Excel user, then you'll click download it as an Excel file. And this should work either in Google or Excel. This picture here is a static picture. This is a picture I screenshotted from StatKey for these numbers, so they will not reflect any numbers you change. So Excel doesn't easily make graphs like this based on numbers over here. So I couldn't make that happen automatically for you, unfortunately. I wish I could. And then I give another example down here. So this one up here is where somebody tells me what the mean and standard deviation is, but they don't show me the data, which happens sometimes. And then down here, I actually have the data, and so I can calculate the numbers. So there's two different problems on this page here. So if you want to give this spreadsheet a shot, go for it. And this one's designed at the top, you plug in your mean, your sample size, your standard deviation, and your confidence level, and then the computer has formulas to make all the calculations you need here, okay? So for example, it says this is a critical value here. That is what I called back here the t-score. So let's rename that critical value is another name for that. And I did ask you guys to reread, excuse me, chapters 8 and 9, because before we had my annotated version where I crossed out a ton of shit. And now all that stuff I crossed out, we're gonna reconsider. And that's what these formulas are here that I was putting into that flow chart. And again, I will publish that flow chart this afternoon in an announcement. So that would be a good thing to put in your notes. All right, we're at the end of time, but I'm gonna do one more example if anybody wants to hang out. I think I'll do a hypothesis test next, unless somebody else has a request for something else. I'll wait 1 minute to see if there's any requests, otherwise I'll pick. Okay, so there's no requests popped up, so then I'm gonna pick a problem. So I'm gonna pick a hypothesis test. And again, the point of these notes is the big stuff that we've been working on for this whole last 5 or 6 weeks from probability on up is this idea of inferential statistics. We're just scratching the surface on inferential statistics. We're only doing confidence intervals or hypothesis tests for means or proportions. There's tons of other things one could test and measure, but we're only doing these. We only have these 10 weeks to do it. The good news, this is a review of stuff we did before, but we're doing it slightly different, so that's the bad news. Other good news is there's no critical thinking assignment like usual this week, and there's no application assignment like last time. It's just pretty much practice problems and then type up some notes or write up some notes for yourself. So, new page, let's do a hypothesis test. New page, there we are. All right, which one do we want to do? So confidence interval, confidence interval, confidence interval, and then hypothesis test, okay. And so we have T's and P's here. Cats now. Oh yeah, I think this is a good one to do. Yeah, let's do the night student one. So this is number 9. Now, when you might have a slightly different version of this. It's either going to say the mean GPA of night students is greater, or the mean GPA of night students is smaller, or significantly different. So you may get a left tail, a right tail, or a two tail on this problem. So this is one I'd recommend doing more than once if you wish. And the computer will remember your high score. So don't worry about redoing it and getting it wrong if it's a slightly harder version. So mine is significantly different. I'm glad to see that because that makes it a little harder. And then I have the data here, but I also made the calculations for you. So I calculated X bar and I calculated S. Since I have the data, I could use StatKey. StatKey only works if you have the data. If somebody just says, hey, here's the mean and the standard deviation, StatKey, that's not enough information for StatKey to do a hypothesis test. using the simulations we did before. Okay, so what do we got going on here? We're testing a claim. Okay, hypothesis test. Mean GPA. Okay, mean. So when we consider our branching of what we know so far about statistics, we're in the hypothesis test section, and we're in a mean. So the question is, do we know the standard deviation of the population or we don't? And usually it's in the I don't know category. And then also, if you have a small sample size, I should add that here too. So small, come on, pen. There you go. Or, you don't know, I should say and or. Okie dokie. So back to that new page. Okay. And then I'm just going to copy all of this into my notebook. On paper, don't write those numbers down, okay? You may copy them into a spreadsheet, and I'll do that in a sec too. So I'm just going to take a screenshot of that much and run through how to do this on a spreadsheet. All right, so according to my cheat sheet flowchart there, I have, let's see, how many people? 40. Okay, that's not small, but anywhere in here, do you see the standard deviation of the population is blah, blah, blah? So let's read it again. Test the claim that the mean GPA of night students is significantly different than 2.8 at the 5% significance level. And they say, pick the hypotheses. Is it left, right, or two-tailed? And then there's 40 people here with a mean of 2.914 and a standard deviation of 0.096. Nowhere here does it say anything about the standard deviation of the population, which even though the sample size is greater than 30, I have to use a t-distribution. Okay, so right away, I have, oops, pen, I have no population STD, right? So that means, again, sigma not known. It did not come out right. There we go. Which means I have to use a t-distribution. All right. So I got to use a t-distribution here. So to use a t-distribution, you need to take the data and turn it into a t-score. So find t, that's supposed to be a t-score. And a t-score is like a z-score. Remember, a z-score is the number minus the mean over the standard deviation. So in this case, the t-score is going to be our mean, so x bar, minus the population mean, that's given up here. And then you want to divide that by parentheses, the standard error, and that would be s over the square root of n. And that's not a very good s, a little better. Okay, so like a z-score, this is a t-score, and notice it's got x bar minus mu, which we've done before for z-scores, but we just, instead of dividing by sigma because we don't know it, we divide by s over the square root of n because we're doing a hypothesis test. So for me, that means I need to take that 2.914 minus the questionable population number there, 2.8, and then divide by, I was given, oops, divide by the sample standard deviation, 0.096 over the square root of 40. And all of these parentheses are necessary here in between. So sometimes this is written stacked, but I like it not stacked because that's the way it goes on calculators. Okay, so other things. I need to identify hypotheses. So let's think about this for a minute. Test the claim that the mean GPA of night students is significantly different. Okay, so different means not the same, not equal. So this sentence up here, translated into English, says mean, mu, significantly different, not equal, 2.8. Now, since this has a not equal in it, this must be the alternative hypothesis. So let's highlight that. And this is something we all struggled with, identifying which one is the null hypothesis and which one is the alternative. And the trick is to analyze the English of the claims you were given. If one of them has an equal sign in it, it has to be the null. If it doesn't have an equal sign, and this is a not equal, so that counts as a that's not an equal sign, it's not equal, then it's the alternative. So which one of these here has an alternative that is mu not equal to 2.8? And for me, it's this one. Now yours might have said, test a claim that the mean GPA of night students is more than 2.8, okay? So if yours had instead, so let's go down here and suppose yours said more than, and maybe it wasn't 2.8, maybe it was like 3.1, then that would translate in English as mu is greater than 3.1. Since there is not an equal in that statement right there, this would have to be the alternative, okay? And then there's a couple of options for the null. The null would either be equal to or less than or equal to. And different people take different poses on that based on the situation. So this one right here is the only one that works for me. So I would check that box right there. And since it's a not equal to, that is a two-tailed test, which makes my p-value a little bit more complicated. And then if I wanted to, I could enter this data into a spreadsheet to confirm these numbers, but I was already given them, so I don't need to recalculate them. I trust that they were calculated correctly, but if you don't trust that, feel free to redo it. All right, so I need to make that calculation. That gives me my t-score. And so what's the point of the t-score? Why do I find that? So I'm gonna draw y here. And StatKey kind of did this automatically for us before. So this axis here is for my t-scores, not the actual numbers in the GPA, but I'll fill them in a minute anyway. The middle for t's like z's is always 0. I need to calculate this number. Since the sample is bigger than what was expected here, this is going to be a positive value. So make a quick note of this, 2.914, 2.8, 0.096. All right, I got to type all that into a calculator. Actually, spreadsheet would be the way to go here. Let's put this in a spreadsheet, new tab, and I'll label that later. Might as well grab the data while I'm here. When I should have started a new video for this. I guess I'll split them later. This is night school. Oops, missed a letter. GPA and paste. And then underneath here, I'll get the sample information just to double check. N equals X bar, sample mean equals, and then S equals. So count. Yeah. Oh, I'm still online. Oops, sorry about that. All right, so there's my count. Average. And STD, oops, equals STD S sample. And if I round those should be the same numbers I was given. 2.914 is 0.096, yep. And I don't need that many decimal places visible. Okay, and these are 3 decimal place values because the data was 2 decimal places, the way I chose to round them that way. All right, so then I need, so that's from the sample. Next is sampling dist. And this is a t-dist. So I need the t-score, which is often called the test statistic. Test statistic, as opposed to the sample statistic. So the sample statistic is the X bar. And then I also have information about the population, right? Population, like the null hypothesis, that would be called the mu. And there is a way to get the symbol mu in there, but I'm too lazy to do it today. Mu is given as what for mine? I think it was 2.8. And that's all they gave me about the population. So this is also my null hypothesis too. Okay, so let's calculate that test statistic. So I said use parentheses when you do this. So parentheses, take the sample mean minus the population mean, divide by another parentheses to get the standard error. And so that's going to be S over the SQRT of the sample size. Close the square root, close the denominator, and Google is better at guessing at your parentheses. If you don't put them in the right spot, Excel just flips out on you and says error. So make sure you end stuff in the right spot. I think that's good. I get 7.48 for the t-score. Whoa, that's huge. Think about z-scores. A z-score of 3 is pretty big. So that's gigantic. Wow, make a note. Okay, so my drawing. So normally with a t-scores are a little wider than a normal t-distributions are a little wider. So with a normal distribution, we usually go like 1, 2, 3 standard deviations are about here. T-distribution spreads out more than that. So it's going to be more like 1, 2, 3, 4. And t-distribution's width depends on how many numbers are in the sample. So the more numbers, the narrower it is, the fewer numbers in the sample, the wider it is. So my guess is that 7, a t-score of 7 is way out here in the fringe. So 4, 5, 6, I'm thinking this is 7 for a t-score out there. And then we want to calculate that tail probability. I mean, that's going to be like my p-value, my guess here, since 7 is so far from 0 for standard deviations, I'm going to think the p-value is going to be about 0. So to calculate the p-value, we needed this t-score right there. I showed last week how to calculate kind of a p-value with the norm.dist. So here we're going to use, I think it's called the t.dist. I better look that up on my spreadsheet. So after I get the test statistic, I'm ready to find the p-value. And that should be t. There's no t.dist. Oh, there we go. T.dist. I think I want this one right here. Left-tailed students t-dist. Left-tailed. What's this? The two-tailed students t-dist, or the right tail. Okay, my number is positive is to the right. I'm going to go for the right tail. I'll try the two-tail in a minute too, just for fun. Okay, I want to know what's your x value, and x is the input, which has to be a t-score. So my t-score is above, comma, and then degrees of freedom is always 1 less than the sample size. And I wish they would say that here, but they don't. So that's going to be an n minus 1. So here's n up here, minus 1. And then enter. Ooh, that's a wicked, it's almost 0. Look at that's wicked tiny. I can't even count all those zeros. Let's copy that. And can I paste it in here? So let me see, what did I type? I typed t dot, that's a funky t, try again, Gary. T dot dist dot right tail. I think it was just an RT maybe. Is that true? Yep. And it wants to know what is your t-score, which is this calculation there, comma, what's n minus 1. And mine was, can I paste it in here? Yes, this wicked small number there. All right, so I was guessing it was about 0 because I thought a z-score, again, is like a t-score. Usually data is within like 3 standard deviations, maybe 2. We're at 7. Now, this is a two-tail test, right? So whatever happens out here, I have to reflect to the other side. Because this is, again, a two-tail test, we have double tails. And most people had trouble with this way back when we were doing these hypothesis tests because they say they forgot their other tail that they're supposed to mirror out here. So that would have to go with a value of -7. T-distributions like a normal dist are symmetric. So my p-value is actually 2 times this because it's a two-tailed test. So fix my spreadsheet. So to calculate my p-value here, I actually have to go back here in my formula and multiply it by 2. Okay, but it's still wicked small. It's like 0. So if somebody said, hey, what is it to 3 decimal places? It's 0. What's it to 4 decimal places? It's 0. What's it to 5 decimal places? 0, 6, 0. It's 0. There's such a remote chance of this happening. What does that mean? All right, so this number has to be times 2, which is still about 0 to 3, 4, 5, 6, 7 decimal places. Help. There we go. So back here, what's my p-value to 2 decimal places? 0. All right, what does that mean? So if you get a tiny p-value, that means there's something wrong with the null hypothesis. And the null hypothesis says night students have a GPA of 2.8. We think it's different. Now our sample says it's bigger, okay, but that wasn't our alternative hypothesis. Our alternative hypothesis is different. So my conclusion would be there's sufficient evidence that the GPA of night students is not 2.8 on average. It's something else. Okay. So that's 0. We're rejecting the null hypothesis, and I didn't ask for a conclusion here, just the decision. Ta-da! And we did it. Whew. All right, that's enough for now. I'm going to find a way to split this video into 3 parts, probably the overview, the confidence interval, and then the hypothesis test. And I'm going to do more of this tomorrow and the next day and the next day. And we'll probably do one on Friday too, since we're getting ready for the final. So stay in touch, do good math. I'll see you soon. Ta-ta.